Good morning. Welcome to Krishna's class. In this talk, we look at some consequences of the Hahn-Banach theorem. And in the last lecture, we have considered the Hahn-Banach. Now we look at some of the consequences. Now we have a couple of theorems in this regard, and then we want to make some remarks about the class of linear functions on a space. So that is going to be. So let me make a statement of this is one of the consequences. Let M be a linear subspace of a normal linear space and let x naught belong. So this is what is given. X is a normal linear space and M is a subspace of that, and x naught is some element of x. So we are essentially it's a characterization of whether this x naught is a limit point of M or not. So this is the characterization. Then x naught belongs to M closure. That means it is a limit point of M. If and only if there exists no linear functional, no bounded f on x such that fx equal to 0 for every x belonging to M, and f of x naught So that's a statement. Okay. Essentially, the problem is this. This is your x, and this is your M. Now, talking about bounded linear functionals on the normal linear space X, and M is a subspace. Now we are taking a point x naught belonging to M. X naught may be anywhere in X. So we are looking at the status of this x naught, whether it is a limit point of M. So that's the question that we are. So it says that it is a limit point of if there exists no bounded linear functional f on x such that fx equal to 0 for every x belonging, and f of x naught is not constant. The other statement is x naught belongs to M closure if and only if there exists no bounded linear functional f on M such that fx equal to 0 for every x belonging to M. Okay, let us prove it. It's very easy. Now first let us take the situation when x naught belongs to enclosure. Assume then we prove that for every bounded linear functional, f with the property that fx equal to 0 for every x belonging to m, fx naught is also equal to, so we prove that if f is a bounded linear function on x such that f of x equal to 0 for every x belonging to m, then this is very simple because x naught belonging to m closure, we are giving it, implies there exists a sequence xn contained in m such that norm of Sn, the sequence xn converges to Sn. Now look at f of x equal to, now we look at this. So f of x naught is equal to limit n tending to, that means modulus of goes to 0 as n tends to infinity. What's the meaning? And you will see that f of xn is 0, that means modulus of goes to 0 as n tends to infinity. Since there is no n involved, this is if and only of x naught. That's what we wanted. Okay. Now here we have to observe that since f is a linear function, say contiguous that facilitates this because it says that limit so the boundedness of the linear functional is synonymous with continuity of the and therefore that is how we do the complex. Suppose uh, suppose there exists a bounded functional f on x and here we need a little bit of minor computation. Now x dot does not belong to guys. The distance from x dot to x is positive greater than a certain delta positive. For some delta. That means this is there is a positive distance between x dot and that is the meaning of it. So now let m prime. See, what we do is we show that there is an f which is 0 on m and which is not equal to 0 at x dot, or by simply extending this f identically equal to 0 to x dot in such a way. So there is such an extension exists. Okay, that's what we want. So let m prime span off and x dot. This is a subspace. Okay. Now define f of x plus equal to lambda. So what is this element? See, note that x plus so here of course x belonging to x plus lambda x dot is a typical It's in M. So it's an element in M plus a scalar multiple of this one. So that will give you that, make sure that it is in the span of this. So any element in the span of this is of this form. Okay? So that's the representation. And we are assuming, or we are defining f x plus lambda x dot lambda. That means we are taking fx equal to 0, x belonging to m, and f of lambda is an element of Now let us do the bit of computation and show the existence of an f with a sad block. So we have norm of x minus x naught is greater than that for every x belonging. So x naught is the minimum distance, delta is the minimum distance from x naught to m. That is the meaning of it. Okay. Now we use this. So this implies, suppose I replace x by minus lambda inverse x. This is also greater than. Why? Because if x belongs to m, lambda inverse x also belongs to m. Therefore, this is an element of m, and you are just writing down this equation. Okay? Because so that is there. Now we will do some estimation. Just a mere manipulation. So you have, therefore, multiply on both sides of this inequality by mod lambda. Mod lambda is norm of minus lambda inverse x minus x naught. This is greater than minus mod lambda. Just multiply by mod lambda on both sides. So we take lambda naught. Then what do you get? See, you can take this inside. Okay? That is mod lambda delta is less than or equal to norm of so this, if you take this inside, then you see this becomes 1 and you get x plus lambda. That's what you get. And what is this? Lambda, mod lambda is essentially f of or f mod f of Now this implies what? This is true for it's a linear functional on M prime which is bounded. Most monopole. Now f x is identical to and f x naught so this is what we have. So what we have done is from M we have extended or discovered a linear functional under the given conditions which is 0 on M and just at x naught it is not equal to a bounded linear function. So what do we do? So we have gone to construct this is M prime. Now from there we will now use the and Banach theorem to extend f onto all of x. Such an extension exists is by HBT exists a bounded linear functional on x does not vanish so that completes the proof. Okay, so that completes the so that is essentially demonstrating how one applies the Hahn Banach So we look at another because see essentially what we have been trying to or the help of the Hahn Banach theorem is take some subspace on which you can take a linear okay, and take an element which is not in that subspace. You can extend this to the space spanned by this M and that set consisting of the singleton elements. If it doesn't cover the whole of X, you can continue this process. That's what we have seen. Eventually, we have shown that you have an extension. Okay, where this capital F restricted to this M would become the, if you call the capital by denote by capital F the extension of F, then that capital F is on M is going to be smaller. That is the extension possible we have seen. Take another thing. Which again uses Banach. Let X be a non-linear space and X naught belongs to bounded linear function of norm 1 with here again, see, look at the what a linear function or how do you get an extension of a linear function? You have x, this is your role of x, this is your m. On m, see, it may be easy to define a linear function on m. You can even keep this m as a finite dimensional vector space or even a one-dimensional vector space and a zero-dimensional space, and that linear function of 0 there, and then start defining with one element added to it, and you will get, so essentially you will be starting with a one-dimensional vector space, right? Now, what this theorem says is that if x naught is an element, then see you can find, suppose x naught is here, then what you do, how do you get the linear function defined there? You take m union x naught. On that you take a linear or define the linear function f of x plus x naught. Define this as so that at x naught can be obtained from here by putting x equal to 0, which is in m, and lambda equal to 1. Then you get f of x naught is equal to norm of x naught. Okay? And clearly, the norm of f is going to be 0. Now that's the arc. So once you do that, then you have an extension of this to the whole space. So once you get your f here, then you go make it to the f, so that f restricted m prime is going to be small. That is a start. So again, we are using Banach. So once you understand the geometry of the Banach extension theorem, then it's quite easy to grasp what is that. So proof. We start with x. Take m to be lambda x naught. K is either R or C. Okay, it's a real space or a complex space. Now define f of norm of then F is a bounded linear function on M with equal to 1 and f of normal function. And that's quite easy. Now what do you do? Extend this to the whole space. So you know that by Hahn-Banach theorem, you can extend this to the whole space, preserving the norm. Okay? To obtain its extension, say f itself, such that norm of f of so that is the existence of, so the extended linear functional is capital. So these are the two applications that we do now. So we make some. Later on, I hope to do another theorem, which is also called the Hahn-Banach separation. So let dominant over K. K is either R or C. Accordingly, we will call it a real normal linear space or a complex normal linear space. So we define, now instead of looking at a single bounded linear functional, we look at the whole class of bounded linear functionals. So let x star, the set of all f, where f is a bounded linear functional on, so the collection of all bounded linear functions. You can prove this. F plus g, suppose f and g are two elements of this, f plus g of x equal to define addition like this of two elements f and x star, then See, the right hand side is very well defined, and this defines it, and you can easily see that if F and G are functionals, then F plus G is also a functional. It is well defined because you are working in the realm of a linear space. Therefore, all these addition, etc., sense, and also scalar multiplication. Therefore, you see that X star is closed with respect to addition. X star is also closed with respect to scalar multiplication. Therefore, it's a linear space. Okay. So, now we define a norm on this. We call the following. We have to define by supremum of this is a standard definition of the norm. Next. Okay. So if you want, you can. Okay. That is also a norm. Okay. Now we claim X star is a what we have to do to show that. So we claim that it's complete. So you start with a sequence Fn which means that norm of 1 epsilon I'll write it this way. That is what we mean by it's a coefficient. But you immediately observe that the sequence Fn(x) for a fixed x. Is a coefficient. Why it is so? Get f of term of x. Okay. So functions term of x. So instead of epsilon that you have there, instead you take epsilon by now, and x is a fixed element. Therefore, this is okay. Therefore, which implies it's a Cauchy sequence in. Now, what you have, k is either R or C. So, k is complete. Both R is complete, C is also complete. Therefore, you see that equal to sum now define f and this side depends on x. Fine. So now run x over the whole of x. Then this finds a linear function this you have to prove because fn's are all linear functions, therefore this is so. So you define that's the outline of the proof. Okay. That's the outline of this is easy. Thus, I mean that does not depend on whether X is complete or not does not depend on that. But this essentially uses completeness of K. So that is the crucial. Now we make some observations. X star is not trivial. That means consisting of only the zero as well. X is the is X star zero whenever X is not equal. Another property that X star has another property is that it separates what do we mean by that? This means given x1 belonging to x, x1 not equal to x2, there exists f belonging to x star such that f of so this is the meaning of this. So we have to actually do this. Give a quick proof of this, right? And this is not equal to by the previous theorem, there exists an f belonging to such that which is possible. But that is using linearity. Therefore, is f of x1 is not equal to f of x2. So we can also have the following. Go back from x star to x. Okay, do it like this. Define now of x equal to see, this is like writing. You are taking x of f to write as f of and then defining a norm for this. How do you define the norm? So what? Okay, that is what we are doing here. Okay, so this is equal to so this is the explanation. That is x star, if you designate by x double star, is the dual of now what you have is this. So to see that x is embedded in x double star. This is because I said at the beginning that x need not be complete, but x double star is anyway complete. So this is a complete space. It's a completion of x. Okay. So we start with a non-linear space which need not be complete. Then you go to x star is complete. Then you go to x star star, but that x star can be identified with x star. So this is the scenario that. Okay. So what you have is this. Pure AB. This is what you have. Okay. So what one does is this. You have another x double star with the property that x, this is your f, this is your f max is this. Okay, right? So you have this is equal to X of. So this X can be identified in call this X. Okay. Or if you want, you call this X star star. That means you are identifying X. But what happens is that unless you have already the completeness of X, if X is complete, then X is equal to X and X double star can be identified. Not, it cannot. Okay. So that's the sort we have. X is embedded into X double star. They are equal. X is equal to now you see the whole functional analysis centered around this kind of problems. This is a X star is the dual of X, X double star is the dual of X star, and X double star is essentially can be identified with X in the sense that X is embedded in X double star. Need not be the whole thing, but it is the whole thing provided X is. So that's what I wanted. Thank you. Now all that I want to do is possibly is a Hahn Banach separation. If you have two convex sets which are not intersecting, then you can find a linear function separation. Okay. So here we have said we are separating the 2 points. Now we can do this with 2 convex sets which are not convex. This is the Hahn Banach separation. That will. Thank you very much.